Have you ever considered what keeps schools, hospitals, and office buildings breathing properly? Unrestricted airflow is important. We see examples all around us. In order for HVAC systems to operate efficiently, the system must be well designed and properly installed to meet the needs of the building occupants. An efficient HVAC system equals cost savings and improved indoor air quality. We know because we're AMCA, the Air Movement and Control Association International, and the International Authority on Air System Components. AMCA is the premier not-for-profit international association of air system equipment manufacturers for industrial, commercial, and residential markets. Major elements of AMCA International are the Certified Ratings Program, research and testing, and education about HVAC equipment selection and installation, including system effects and its causes. System effects can be described as fan performance loss, the detrimental effect on fan air performance due to adverse flow conditions at both the fan inlet and the fan outlet. In addition to adversely affecting fan performance, system effects can also increase noise, increase vibration, and cause premature impeller or bearing failure. When designing buildings and air systems, minimizing energy use is of the utmost importance. The emphasis must be on eliminating system effects, rather than simply identifying and accounting for them. Quantification of system effect is necessary to evaluate improvements to existing buildings. For optimum system performance, the airflow at the inlet must be fully developed, symmetrical, and free from swirl. Ducting on the outlet needs to be designed so that the asymmetrical flow profile from the fan is allowed to diffuse and approach fully developed flow. The effect on fan performance when these conditions are not met is called system effect. You can master all the theories about how to design and specify systems to move and control air efficiently, but until you actually build and install the components, you won't really be able to understand how seemingly small changes in execution and installation can have a dramatic impact on the performance of the system. Therefore, it is important to understand system effect, because of the significant impact it has on the efficiency and operating cost of the systems you design and build. System effect at the fan inlet and outlet seriously impacts airflow. The first major impact involves proper fan inlet design. As stated earlier, the airflow at the inlet must be fully developed, symmetrical, and free from swirl. Non-uniform inlet flow is the biggest cause of system loss. Factors adversely affecting inlet flow are insertion of obstructions, elbows and dampers too close to the fan inlet. Let's assume we use an open inlet as a benchmark, with the inlet velocity set to 1 inch of water velocity pressure. If we affix a poorly designed right angle inlet box directly to the inlet side of the fan, our velocity pressure is reduced to just 0.6 of an inch water, a 40% reduction, which equates to a 23% loss of airflow. If we improve the design by adding turning vanes to the inlet box, we improve the velocity pressure to 3/4 of an inch water, but that's still a 13% loss of airflow. Changing the inlet box to an elbow will help. Properly installed, a sweeping radius elbow can result in only a 3% loss of airflow. A good rule of thumb is that elbows near the fan's inlet should be radiused and include turning vanes when located within 3 duct diameters upstream of the fan, recognizing that mitered elbows with or without turning vanes can cause system effect even when located up to 5 duct diameters upstream. The second major impact involves proper fan outlet design. The same elements that have an impact on inlet design, namely ductwork and dampers, also have an impact on outlet flow. Let's assume 1 inch water velocity pressure on the outlet side of a fan, similar to the inlet side in the example just given. If we add a right angle elbow on the outlet side in the direction of the fan's rotation, we reduce the velocity pressure to 0.85 of an inch water velocity pressure, which is an 8% loss of airflow. However, if we change the direction of the elbow to opposite that of the fan's rotation, we reduce it even more to 0.7 of an inch of water velocity pressure, which is a 16% decrease in airflow. So major ducting inefficiencies can occur on both sides of the fan. One must also remember that a major additional factor is the length of the ductwork itself. You should always strive to achieve 100% effective duct length. Ducting on the outlet needs to be designed so that the asymmetrical flow profile from the fan is allowed to diffuse and approach fully developed flow. The point where this is achieved is referred to as 100% effective duct length. A good rule of thumb is that effective duct length is 2.5 duct diameters when duct velocity is 2,500 feet per minute or less, with 1 duct diameter added for each additional 1,000 feet per minute. Testing in the AMCA lab has shown that a centrifugal fan needs 100% of effective duct length to avoid system effect, while a vane axial fan needs 50% effective duct length. So remember that in a ducted inlet, ducted outlet installation, system effect may occur on both sides of the fan. What is so striking about system effect is the power required to overcome it. A 10% increase in speed requires about 33% more power, and with increased power come increased costs. Here is the formula for calculating the operating cost of a fan. For example, assume a fan with 20 brake horsepower running 16 hours per day for 251 days per year. At 15 cents per kilowatt hour, the cost of running that fan is nearly $9,700 per year. If we increase that fan speed 10% to compensate for system effect, our new operating cost is nearly $13,000, which is an increase of approximately $3,200 more per year. And that is just for system effect that impacts the inlet side of the fan. Or consider a second example of a 100 brake horsepower fan that costs $50,000 per year to operate. A 10% increase in speed to compensate for system effect will result in an over $16,000 operating cost increase per year. And that's just for one fan. In addition to cost increases, there are other real dangers to be considered before simply increasing the speed of a fan to overcome system effect. Certain structural elements affected by fan speed can fail catastrophically if the maximum safe speed of the fan is exceeded. Make sure that the electrical equipment is capable of handling the increased power requirements. When fan speed is increased, you can expect both the fan and the system's fittings to be louder. Additionally, there will also be increased duct and fitting leakage. The bottom line? When designing and building systems, always be aware of the economic trade-off between increased fan power costs and shrinking the size of mechanical rooms to increase income from revenue-generating floor space. Quite often, increased revenue may not offset the added power costs. It may seem like a good idea to reduce mechanical space, but it can be a very costly decision. So, remember these simple recommendations to minimize system effects. 1. Allow enough room as necessary in the building design to avoid system effect when connecting fans to the duct system. 2. When space or other factors dictate a less than optimum arrangement of the fan outlet and inlet connections, use only accessories and appurtenances that do not create significant system effect. 3. Include adequate allowance for the effect of all accessories and appurtenances on system and fan performance. System effects can be quantified, however, in the new world order of building green, high-efficiency building designs and net zero energy use buildings. The system effect in new air system designs must be avoided. For older and currently built systems, AMCA Publication 201 provides a means for evaluating the system effect magnitude to identify sources for energy reductions through system improvements. You can order AMCA Publication 201 on our website at amca.org. Remember, buildings have to have ventilation. Ventilation requires fans. It's important to reduce power consumption with any system. System effects need to be avoided. AMCA assures products perform as stated. AMCA is a valuable resource for engineers, architects, contractors, and building owners. AMCA is excellence.